Hello, this is Richard Hammack's Calculus 1. We are in part 5 of the course on integration. This is lecture 41b, Other Formulations of Definite Integrals. It's a continuation of lecture 41a, in which we introduced one of the primary ideas in calculus, the definite integral from a to b of f of x dx. By definition, it equals the limit as n goes to infinity of a particular Riemann sum. We didn't evaluate any of these limits explicitly in lecture 41a because, as we mentioned in lecture 42 on the fundamental theorem of calculus, we'll have a quick way of computing these numbers that avoids the limit. However, the limit is a crucial part of the definition because it gave the definite integral meaning. For one thing, we have an area interpretation thanks to the limit. Also, the limit was a gateway to developing lots of properties of definite integrals that we examined in lecture 41a. Our goal today is to look at some other ways to define the definite integral, some slight modifications to this limit definition. This is actually not going to be used for the rest of the lectures in this series, so in that sense you could skip this lecture and you're going to be okay. However, depending on what textbook you're using, what we talk about today may help make what's happening in the lectures match up with your textbook. And it's also a topic that you might need in subsequent classes. I'm going to talk about three different definitions of the definite integral. All three are pretty similar to one another, but they have some minor differences. Let's begin by reviewing the definition of the definite integral from lecture 41a, and I'll call this definition 1 of the definite integral. The setup was we had a function y equals f of x defined on an interval from a to b. And we defined the definite integral from a to b, f of x dx, to be a certain number, which we get at as follows. We first take an integer n and divide the interval from a to b into n equal-sized pieces, each of length delta x, which equals b minus a over n. This chops up that interval into equal-sized pieces, and we sometimes say that's a regular partition of the interval. So in this definite integral definition, we'll call it the definite integral with regular partitions. And we'll have irregular partitions later in definition 3, but we'll get to that. The next thing we did is we gave numeric values to the grid points. For any k between 0 and n, x sub k equals a plus k times delta x. So x sub 0 is right there at a, then x sub 1, x sub 2, and so on down the line, all the way to x sub n, which equals b. The next thing we did is for each subinterval, we went all the way over to the right to that grid point, took f of that, and that gave us the height of a rectangle whose base was delta x. And we did this for each x sub k, took f of x sub k to get the height of a rectangle. In so doing, we get n rectangles that approximate the curve. For each rectangle, say rectangle number k, it has a height times base, which is f of x sub k, which is the height, times delta x, which is the base. Then we form this Riemann sum, the sum from k equals 1 to n of f of x sub k times delta x. That Riemann sum is just height times base for each rectangle, all added up for n rectangles. Then we let that number n, the number of rectangles, get bigger and bigger. And as that happens, this Riemann sum, it still represents the sum of those many, many, many different rectangles, or the sum of base times height for them. The delta x, it gets smaller and smaller the bigger n gets, but you've got more and more terms in the sum. And the limit as n approaches infinity of that Riemann sum is what we define the definite integral from a to b of f of x dx to equal. So this was our first formulation of the definite integral. And we noted in lecture 41a that this limit could be possibly negative or positive or zero, because f of x, it may be sometimes above the x-axis, other times below. So the base times heights of these rectangles could be either positive or negative or zero. But this is the definition that we've been using of the definite integral. And I'll continue to use this definition in lectures after 41. But just for completeness, I want to talk about two other definitions of the definite integral that you may see in the future depending on what math courses you take and what textbooks you use. Here's a second, slightly different definition of the definite integral. This is called the definite integral with regular partitions and sample points. So the setup is exactly the same. We have a function y equals f of x defined on an interval from a to b, and we're going to define the definite integral from a to b f of x dx. In this second definition, we start out exactly the same way. We divide the interval into n pieces, each of length delta x equals b minus a over n. We set up some grid points, just as we did before, so that hasn't changed. But then what we do next does change. We are now going to, in each subinterval, take what we call a sample point, denoted by x sub k star. And that sample point, x sub k star, is a sample point that's in the kth interval. So for the first interval, we're going to take a sample point x sub 1 star. And that x sub 1 star, it could be anywhere in this interval that you want to put it. X sub 2 star is going to be the sample point of the second interval. And it could be anywhere in this interval. All the way over to the right if you wanted it, all the way over to the left if you wanted it, right in the middle, or anywhere. It's just a sample point. Then we take the third sample point and the fourth, and so on, all the way up to the nth sample point. Now, in making the rectangles, we're not going to take f of x sub k to get the height. We're going to take f of the sample point. So we have a sample point in each subinterval. And for, let's say, the first sample point, we take f of that. We get the height of the rectangle, and there's our rectangle. Then we take f of x sub 2 star, and that gives the height of the second rectangle. F of x sub 3 star, f of x sub 4 star. This is how we get our rectangle heights, all the way down the line. So for rectangle K, it has a height times base, which is f of x sub k star times delta x. That's height times base for any rectangle K, for K between 1 and n. We can then make a Riemann sum, the sum from k equals 1 to n of f of x sub k star times delta x. This is exactly like the Riemann sum that we had in our previous definition. The only difference is we have an x sub k star here, a sample point, whereas in our definition 1, we always took that sample point to be way over here at x sub k. And we didn't even call it a sample point. But technically speaking, you could look at definition 1 that we just saw in the previous slide as being definition 2, where the sample points are chosen to be all the way to the right. But anyway, with this definition, the definite integral from a to b f of x dx is defined to be the limit as n goes to infinity of the sum from k equals 1 to n of f of x sub k star times delta x. So it's almost exactly the same definition that we started out with, but we have a little bit more flexibility here to choose our sample points. I'm going to move on to one final definition of a definite integral, definition 3. This is the definite integral with irregular partitions. And this is our most general definition of the definite integral, and the one where if you go on to take advanced calculus, you'll be using. Here's the way it works. The background is the same. We have a function f defined on an interval. And the first thing we do is we make a so-called partition of that interval. We chop it up into n subintervals with grid points x0, x1, x2, and so on. But the thing is, these don't have to be equally spaced. You have total flexibility in how you choose them. You just have a equals x sub 0, which is less than x sub 1, which is less than x sub 2, and so on, less than x sub n, which equals b. So those are your grid points. Next, you take a sample point in each grid point. So in the kth subinterval, the sample point is x sub k star. And that could be anywhere in that subinterval. And then, you guessed it, with those sample points, you take f of each one to get the height of your rectangle. So f of x sub 1 star is the height of your first rectangle. F of x sub 2 star is the height of the second rectangle, and so on down the line until the nth rectangle. And when you do this, you get a bunch of rectangles and rectangles that have different thicknesses. So delta x is not going to cut it anymore for the thickness or width of these rectangles because they're all different. These partitions are irregular. So what we have to do is keep track of that by giving a special notation for the width or base of any of these rectangles. The base of the first rectangle we denote as delta x sub 1. The base of the second rectangle by delta x2. The base of the third rectangle by delta x3, and so on. In general, the kth rectangle, its base is going to be denoted by delta x sub k. Now for each rectangle, we have a height times a base, which according to the setup here would be f of x sub k star, f of that kth sample point, that's the height of the rectangle, times the base, delta x sub k. And then you can form your Riemann sums. You add up height times base for all of those rectangles. So the Riemann sum in this case is the sum from k equals 1 to n of f of x sub k star times delta x sub k. This is different from our first two definitions because we don't just have one delta x, there's a different one with a potentially different length for every rectangle. But once we make this setup and have this Riemann sum, technically we have a Riemann sum for every n this way, we define the definite integral from a to b, f of x dx, to be just as before, the limit as the number n of rectangles goes to infinity of that Riemann sum. However, there's one thing here we have to be really careful about. All these rectangles have different thicknesses. You have to be sure that the thickness of every single one gets smaller and smaller as n increases. I mean, think about it. You could have maybe the second rectangle stays really fat and doesn't fit the curve, but all the other rectangles, as n increases, they get skinnier and skinnier and skinnier. What we need to have here is uniformly the bases of all the rectangles getting smaller and smaller and smaller as n goes to infinity. So to accomplish that, it's traditional to call the length of the greatest base delta. So the largest base of your rectangles, you're going to keep track of that and call it delta. And we insist in this limit that that largest base delta approach 0 as n goes to infinity. So here the number of rectangles is like before going to infinity, but we also have to rig into the system that the thicknesses of all of the rectangles are going to 0, because we no longer have just a delta x. We have n different delta x's in this setup. So this is how the definition of the definite integral goes in a lot of calculus textbooks. It's a little more complicated, but it's much more versatile and robust. However, for what we're going to do in these lectures, I'm going to just be using the first definition, definition 1, that we initially had in lecture 41A. You might wonder why we would need something like definition 3 with all of these different rectangle widths and sample points. Well, there are a couple of reasons. First of all, in advanced calculus, this becomes important. And I'm not going to go into why it's important, but it is. Take my word for it. And if you ever do take a course in advanced calculus, you'll see why. Another reason that you might define a definite integral this way is that sometimes you could be interested in actually working out the definite integral from the limit. And in so doing, you'd want to make things as simple as possible and use some of the control that you could get in this more versatile setup. And I'll give you an example of that. Imagine you wanted to find the definite integral from 0 to 4 of the square root of x dx. And you want to work it out from the straight limit definition. Let's say the definition from the previous page, or any of the other definitions for that matter. Let's think about how we would do this. The first thing we're going to do is we need to set up our x sub k's, our grid points. However, notice the function that we're going to plug them into. It's the square root of x, and that's complicated. To make life simple, you want your grid points, the things that are going to be plugged into here, to be perfect squares so you can take their square roots. So let's let x sub k, for any k between 0 and n, be 2k over n squared, a perfect square. So in other words, it's 4k squared over n squared. Now, why would we do this? Think about it. X sub 0 would be 4 times 0 squared over n squared, which is 0. So x sub 0 is right there. X sub 1 would be 4 1 squared over n squared, so that's a little bit bigger than 0. And then by the time you work up to x sub n, you get 4 times n squared over n squared, which is 4. And that's the endpoint that you want to end at. So when we let our x sub k's be defined this way, here's the way they look. Here's x sub 1, x sub 2, x sub 3, all the way up to x sub n, which by this formula equals 4. So you've now got your grid points placed in here, and notice that they are irregularly spaced. But that's what you want because they're now perfect squares. They're going to be easy to put into this function. Well, when we do this, of course, we have different lengths of different bases for all these subintervals, all the potential rectangles that we're going to put up here. Delta x sub k stands for the length of the k subinterval in our setup from the previous page, and that would be x sub k minus x sub k minus 1. For example, the sixth subinterval right here has a length of delta x sub 6, which is x sub 6 minus x sub 5. That's x sub 6 minus x sub 6 minus 1. And in general, delta x sub k is got this way. We can actually work that out. Delta x sub k, therefore, is x sub k, which is 4k squared over n squared, minus delta x sub k minus 1, which would be 4k minus 1 squared over n squared here. Combine that into a common denominator and square out the k minus 1 and collect all the terms. It reduces down to delta x sub k equals 8k minus 4 over n squared. So that is the base of rectangle number k. That's delta x sub k. And notice that changes depending on what k is. You can see here that the largest base, delta, is the very last one, which is 8 times n over 4 divided by n squared. That's delta x sub n. And notice that as n goes to infinity, delta x sub n, or rather delta, is 8n minus 4 over n squared, and that goes to 0 as n gets bigger and bigger. You can check that. So this delta, it really is getting closer and closer to 0 as n goes to infinity, just as it should in our definition number 3 of the definite integral. So now let's set up the integral. The integral from 0 to 4 of the square root of x dx, by definition, is the limit as n goes to infinity of the sum from k equals 1 to n of f of a sample point in the kth interval times delta x sub k. And here we're using that last definition of a definite integral. Now remember, we can make our sample point anything we want it to be in its respective interval. Let's slide it all the way over to the right. So the sample point x sub k star is just equal to x sub k. This limit becomes the limit as n goes to infinity of the sum from k equals 1 to n of just f of x sub k, and f is the square root, so that's the square root of x sub k, and then times delta x sub k. Next, let's plug in what x sub k is. And remember, we configured it to be a perfect square. So we get the limit as n goes to infinity, sum from k equals 1 to n of the square root of x sub k, which is the square root of 4k squared over n squared. And this is all times delta x sub k. And remember, delta x sub k is 8k minus 4 over n squared. So we put that there. Clean this up. The square root of 4k squared over n squared is 2k over n. And that's multiplied by the 8k minus 4 over n squared. So we get the limit as n goes to infinity of the sum from k equals 1 to n of 2k over n times 8k minus 4 over n squared. Let's work with this sum a little bit here. You can distribute that 2k over n into the fraction to its right and break up that fraction. It becomes 16k squared over n cubed minus 8k over n cubed. So we have the limit as n goes to infinity of the sum from k equals 1 to n of the difference of these two fractions. And we're going to keep pushing this. The next thing we can do is use one of our sigma properties. The sum from k equals 1 to n of this expression minus that one is the sum from k equals 1 to n of this expression minus the sum from k equals 1 to n of that other expression. So we're breaking this up into two simpler sigmas. Now what can we do next? In this sum, n is, you think of it as a constant. It's going to infinity, but right here in this sum, it's some constant, like a big number. In the sum, we have 16 over that constant cubed times k squared. We could factor the 16 over n cubed right out of that sigma by one of our sigma properties, and the same for the 8 over n cubed. So let's do that. The 16 over n cubed came out and left us with just a k squared, and then minus the 8 over n cubed comes out and leaves us with just a k. What next? Well, remember, we have a couple of formulas, one for the sum from k equals 1 to n of k squared, and the other for the sum from k equals 1 to n of k. You might have to go back and look those formulas up. We don't use them very often, but here's a place where we do use them. Remember, this sum from k equals 1 to n of k squared is n times n plus 1 times 2n plus 1 over 6. And again, that's something we talked about back in lecture 40. Likewise, the sum from k equals 1 to n of k is n times n plus 1 over 2. And that's getting multiplied by the 8 over n cubed. So look at this limit. We're getting rid of the sigmas here, and it's working out to be something that maybe we can actually evaluate. In this first term, let me get the 6 over here under the 16. I'll scoot that n cubed under the other n's here. So we get the limit as n goes to infinity of this expression minus, and let me put that n cubed over here and bring the 2 underneath, so 8 over 2 is 4. So that's minus 4 times this expression over n cubed, and multiply the n times n plus 1 together, and you get an n squared over n here, divided by n cubed. All right, take a look at this limit. The limit as n goes to infinity of this rational function minus this one. Remember how when you have a limit as n goes to infinity of a rational function in n, you can get that answer by picking out the highest coefficients, the coefficients of the highest powered terms. In this case, 2 and 1, and the answer is going to be 2 over 1. So this limit works out to be 16 over 6 times 2 over 1. Then we subtract out 4 times the limit as n goes to infinity of n squared plus n over n cubed. And look at that, the highest power of n is on the bottom. And remember, in such a limit as n goes to infinity, you get 0 for the limit. So the second term becomes minus 4 times 0. Working that out, we've actually got an answer, 16 over 3. So we've just worked out the definite integral from 0 to 4 of square root of x dx using our latest definition of the definite integral with irregular partitions, and we got an answer. It wasn't a whole lot of fun, but we got an answer. And notice that the thing that made this work was the fact that we could use irregular partitions so that we could let our grid points be perfect squares. So when we took the square root of them, it would be simple. Everything hinged on that. So this is one reason you might want to use that definition 3 of a definite integral. But you probably wouldn't want to use it because working out definite integrals like this is a real pain. You can do it in many cases, but it's not a whole lot of fun. This example, if you stayed with me for it, you probably realize this is only for the real serious math students, the experts. You may want to try a few of them like this just to see if you can do it. But take heart. In the next lecture, lecture 42, we'll get to the fundamental theorem of calculus, and you will find there, among other things, a way of computing an integral like this one in just 2 lines. You'd be done with it about right here, rather than working out that limit completely. It's a big topic, it's an important topic, and if you're with me now, I know I'll see you in lecture 42. So have a great day. I'll see you then, and goodbye.